Good morning. My name is Jim Buckwalter, and I'm representing the hardware breakout session panel. Our panel basically identified a number of short, medium, and long-term priorities that would attend to performance optimization, in particular the reduction of power consumption for millimeter wave circuit architectures, optimized to support multi-beam MIMO and or array of arrays architectures. Improving power consumption has several pathways that could be explored over the next decade, including heterogeneous integration of beyond CMOS devices with traditional ASICs for improved millimeter wave performance, as well as working closely and collaborating with signal processing and network researchers to streamline architectures according to network requirements. Our number one priority, of course, would be to establish new hybrid architectures that investigate the role of both analog and digital signal processing to support beamforming. Signal processing will play critical roles not only for forming beams, but also for interference mitigation in the array, as well as potentially linearizing this response and compensating for non-idealities in CMOS at millimeter wave bands. A second priority will be to continue exploring subcircuits such as power amplifiers, ADCs, PLLs for constraints such as power, efficiency, energy per bit, and figure out how these will play into standards that will be associated with upcoming 5G interfaces. We continue to believe that circuit improvements will yield better efficiency as these subcomponents are optimized not only for certain frequency bands and power levels, but also for the waveforms and the multi-user requirements that will develop over time. Our panel believes that more clarity regarding the need for components will be developed through close collaboration with other communities interested in millimeter wave prototyping. A third priority for our community is the recognition that prototyping has not really significantly improved over the past 10 years in terms of cost and time to development. And it continues to plague the entire community as phased array prototypes are difficult to develop and don't reach the researchers that need them. The IC community has developed rapidly around millimeter wave over the last 10 years, but there continues to be significant impediment to future development due to time and money required to produce millimeter wave systems. Two facts were recognized by the panel. First, university researchers will broadly be unable to take advantage of future scaling in CMOS to improve millimeter wave systems, and in some ways have gotten off the CMOS scaling roadmap. A second is that packaging is an incredibly hard problem that continues to plague system development, and we need to seek some kind of standardization so that IC development can feed into certain standard package form factors, and that in the future this is going to be a primary system consideration before beginning any circuit design. There's also a recognition that we need to disrupt the traditional ASIC flow that's been undertaken in millimeter wave chip development, simply because NSF funding can't support any reasonable circuit design or sophisticated circuit design in the future. Our proposal is to develop an IP repository for chip designs developed and funded by the NSF program participants to be shared within or by other NSF program participants in the future, with the goal to greatly shorten development time required for millimeter wave ICs by allowing students to focus on high-level system design considerations rather than standard sub-circuit elements such as LNAs or mixers. This effort might be ultimately very important to changing the way this research is undertaken over the next 10 years. So, with that.
Are there going to be questions? Are there questions for that, or do we just
do the readout and then leave the panel discussion to...
Okay. I think Jim was much more articulate than I am. I'm just going to try to summarize on the fly.
I think we're going to wait. We're going to wait until there's going to be a broader panel discussion.
Will these actually be shared? Because you read stuff up very, very quickly.
Yeah, we definitely will.
Yes.
These folks have it. We'll post it.
Excellent.
Earlier request for a lot of information coming from me, so please don't use your laptops. Two, there'll be panel discussion following this, so let's follow up on our questions.
Okay, so I don't have it so polished as Jim does. I'll just try to wing it as I try to look at the notes that we covered. So I'm Sandeep Rangan. I was representing the communications and signal processing subgroup. That was looking at everything from physical layer techniques up through essentially the MAC layer method. So I think broadly speaking, I would say that a lot of the term there are challenges, but they were more in the short to medium term. So the most obvious was in the MIMO architectures, because the large high-dimensional antenna arrays plays a fundamental role in millimeter wave. The question there is how to do that efficient computationally, and also what types of architectures, analog or fully digital, should be explored. There was a feeling that that was good that at least people from industry had said that this is something, the low resolution architectures is something that is certainly worth pursuing. One of the questions that came up, and we'll return to this when we go through the shared session, is that there needs to be there was a feeling that people in signal processing don't have good models from hardware teams on what are models about the actual power consumption, which is a fundamental limitation. There's also some needs to be much better study of things like blockers and interference. There are good standards in the low 6G specs on what the radios need, but that's not as well understood at the higher frequencies. Moving up from there was still some discussion on waveform design. Again, this is probably something that will get mostly worked out in the next couple of years, especially if the standards come to design. But there's still a question with whether we want to do OFDM or single carrier, and how to address issues like multiple access and PAPR. There was I was surprised there was still a considerable interest in continuing channel modeling effort. The main focus, there was appreciation that the community had made a lot of progress in understanding channels, but some of the key focus areas going forward are the dynamics of the channel, particularly because the blocking events and Doppler are very fundamental to any type of higher level system design. But there's also an interest in understanding the statistics of for macro diversity, that is with multiple access points, because that also plays a fundamental role, at least in the cellular context. There's some other use cases like vehicular channel models, for example, that are not really well understood, as well as also fixed wireless access. There's other minor things like foliage, especially with snow, whether you can do kind of coverage planning tools. And also there's interest to try to develop, simulate like a low-level modeling that could be abstracted up for higher-level simulation. There was also a bit of discussion on prototyping, but I think Jim covered most of that. Then there was going further up, there was the MAC layer. There's still a lot of open questions in the MAC layer, how it's to be designed. The fundamental challenge here was to address the directionality and the very low latency, and while supporting multi-user systems. There's also considerable difficulty in also trying to figure out the feedback. So all of these will definitely play a role. All the other things that were mentioned was how to do efficient hybrid ARQ, and also sub-band scheduling and so on. And of course, another thing that continued to come up a lot was the whole issue of synchronization, beam search, and initial access. That permeates its way throughout the protocol stack and has a considerable effect both on one end on the MIMO architectures that we use, but also through the MAC layer. And there's still some open questions there. Again, none of these are showstoppers, and I think they'll be mostly understood within, at least that's my feeling, within the next few years, but that's what they are. Then we finally concluded with trying to understand a bit of the use cases, and there was a feeling that if we can get better understanding of those use cases, we'll know the requirements we're going after. Some of the use cases that were identified were vehicular, AR and VR, other things which are less understood like aerial and drone. And we briefly mentioned whether we should be starting to explore other things like chip-to-chip and factory automation, which are less understood right now. And then there's a further effort only things that are going much in the longer term is whether we pull up even higher frequencies into, say, the sub-terahertz and what those open up.
Morning. My name is Marwan Kins. I'm with the University of Arizona, and we were tasked to kind of identify some of the key issues from a networking protocol perspectives. But we kind of expanded the scope a little bit to look at also into networking architectures or potential challenges in networking architectures for millimeter wave. So some of these issues kind of overlap with the two other thrusts, in particular with regard to the MAC design. Some of the issues we feel that these are short-term. They can be kind of handled or dealt with by tweaking or extensions of some of the existing work in the lower frequencies. But others seem to be more challenging. There are no showstoppers here, but they would require more work. So one of the big issues seems to be related to, generically I define it as network node discovery and initial coordination. Part of that is computationally efficient beamforming and tracking algorithms. There is some work on this front, but given the highly directional nature of millimeter wave, we feel existing works are still not sufficient to deal with the latency requirement that is needed to address this problem. There was a bit of a discussion about the resource allocation aspects of millimeter wave, both in time, frequency, and space. Hybrid MIMO beamforming came as also a very important issue that some work and more work is needed to look into that. Link scheduling, beam link scheduling is also what seemed to be a very important topic to look into given this environment. We also had discussion about the need for channel modeling. This is something that is not necessarily to be dealt with by networking folks, but lots of protocol designs, particularly at the MAC layer, requires accurate understanding, accurate modeling of the channels, and also better understanding of the interference environment. So it seems like extrapolating existing models, to fit the millimeter wave environment is not necessarily the best way to go. We also seem to have a kind of a shortage in terms of simulation tools that could be used to handle protocol design issues. Many of us are still relying on NS3, which has seemingly a very nice, initial package to deal with millimeter wave. But there seems to be a more need for a more detailed understanding or capturing of the low-level aspects of the interference environment. On the protocol side, going a little bit higher in the protocol side, there seems to be also a need to understand how the millimeter wave networking what implications it will have on TCP in particular. Given that now we are operating in a highly directional environment, latency can be an issue. So there are some ideas about tweaking TCP, but there are also possibilities to look at it from a bottom-up approach and maybe pass some information from TCP to lower layers and maybe design lower layers to somehow cope with the congestion behavior of TCP. Multi-homed, multi-BS environment, handover in these environments seems to be also a very important issue to look into. We also talked about, and this is probably related to the unlicensed and the shared spectrum portions of millimeter wave, the issues of heterogeneous coexistence and spectrum sharing. The implications also on network economics. There seems to be also now, given that there's an abundance of unlicensed spectrum, about 11 gigahertz, there probably be we envision lots of devices that will access that spectrum. So, and these are not necessarily of the same type. So heterogeneous coexistence is relatively a new area, and many people are interested in understanding the implications of such coexistence on interference and on performance. So we also we were also interested in use cases, be it vehicular networks, UAVs, and others, and that would kind of guide further research into what are the challenges when dealing with these specific use cases and what would be the implications on protocol design. And I'll stop here.
I think I was just thinking about it yesterday night. The whole discussion yesterday stemmed around millimeter wave communication. There's also this big thread of sensing using millimeter waves. I don't know if, since this coordination group is supposed to be all about millimeter waves, I was wondering if you guys have any thoughts on what we should do in that frame, in that sense.
Yeah, actually, I was wondering the same question myself. Is that something that's in the scope of sensing? Then definitely there would be other issues that we didn't discuss it, but I've had project conversations, in particular, say, millimeter wave radar, and that's something that our lab and some other, and definitely many other labs are involved with, as one that has a number of signal processing challenges, for example.
Yeah, and I'd second that as well. I think it was brought up in our panel as well. For a large part, I think there are ways to make the hardware reconfigurable between a communication kind of platform and a radar platform today using digital signal processing techniques. So it's something that could certainly be built within the scope of existing and future efforts.
Although we have not really discussed that, but I definitely agree this is a very important issue to look into. In the context of, you said sensing, I guess, right? So some of the ideas that were floated around, whether, for example, full duplex features could be used as a way to kind of, for example, transmit and sense for the purpose of enabling coexistence among different systems. So this form of sensing, I guess, was kind of thought as a possibility, although the implications on hardware, once you start looking into full duplex operation, is still unclear whether this is going to be feasible in a small form factor kind of device.
I think Marwan had mentioned, that wasn't in our group, but I think you mentioned the whole issue of localization technologies as well. I think because you have I thought it was you, but I can't remember. So that's another area that I have in my notes, but I forgot to mention.
I'll just add that I think, channel estimation is a form of sensing that naturally happens in the process. So there's a lot of synergy, and if you look at the development at earlier frequency, it's striking the parallels, MIMO, OFDM, and then, OFDM radar principles. So there's a lot of commonality which could be exploited here. Any other big questions or concerns right now before we started the panel discussion? Are you going to be on the panel, Arun?
Yeah, sorry I missed yesterday. My name is Arun Ghosh from AT&T Labs. Maybe one comment to the signal processing aspect of it. I did hear a lot of good ideas, but I think another one that we should seriously start thinking about is this whole concept of low-resolution signal design for an end-to-end. I know there has been some work on mostly on the receiver side, but what is still missing in all of this is a complete end-to-end system where you can run the whole system with very low resolution. And my thinking is, in millimeter wave, both at the transmitter and the receiver, you have a highly spatially oversampled signal. So does it still mean that even in the time frequency domain, we still need to follow the same way that that we sample the signal? Where sampling in space is essentially the same thing. Doing it in the time domain if you have a very dense array. So that's another area for us to look at as to how we design end-to-end systems in millimeter wave that are going to be very efficient, very low power consuming, very power efficient. And you can essentially scale the system to extremely large number of antenna arrays, which
Yeah, sorry. Right. That's a good point. We did actually mention low resolution. That was certainly part of the MIMO architectures. But you're right when you talk about end-to-end. A lot of the discussion was on the either transmit or receive side of that. But Jim, I think, had mentioned a very good point that was also confirmed by some of the circuit designers that we looked at, that actually even not just in the antenna array, but the interfaces going end-to-end off the chip, for example, and then if one were to implement, say, remote radio heads or any other part, all of those things will actually, the quantization resolution will matter. So that, I think maybe the end-to-end part, I think it's in my notes, it's one of the things I may have just skipped over a little bit.
So I think we also talked about simulation setup, right? So we talked about network level simulators. But clearly, network level simulators rely on some abstractions that happen at the COM level, and the COM level simulators rely on some abstractions that happen at the hardware and the device behavior level. So, do you guys have some thought? Again, these are all different timescale simulators, right? So, you really can't expect them all to work together in a single piece. But any idea of what is the state of the art, what needs to be done to get these abstractions finalized in some sense?
Actually, I'm going to put it to Marco because he was talking about a lot of this with Nadia. If you want to quickly get the microphone on it.
Yeah, so we had a nice discussion yesterday during the networking session, and current simulator has a obsolete abstraction. We agree that it's not enough today, so we agree that we should start communications to try and understand what type of abstraction, what type of simplification of the channel we want to have for a network simulator. So for now, we only use LTE-driven block error rate curves based on the SNR, but we would like to better define beamforming, phase noise, and these kind of very critical aspects for millimeter wave. So to capture them and use them in a network simulator. So that's why we should start an interaction between lower level and higher level simulators to try and have a common platform. So that's, yeah.
Tiaga, you're saying this has to be completed. I think this has to start. So because it hasn't really started. I think we've seen some of that with LTE where the layers, the conceptual layers were blurred. But now with millimeter wave, the whole layering concept is out the window. And I think the critical piece here is what do we want to make available from the hardware circuit all the way to the network. Not everything, obviously, right? Because we can't have the one simulator that can do everything. So understanding what is important to bring up to the various pieces and the various is very important.
Yeah, so I was thinking, right, so for the 2G or 3G system, in 4G system, we are more focused on the bandwidth. So if the bandwidth is limited, we try to get a high throughput or high capacity. Then come to the millimeter wave, we seem to have a lot of bandwidth, and we can get this 10 gigabit per second data rate. But the problem is the link is not reliable, right? So it's on-off, it's intermittent. But the requirement for the application right now is more strict. So we want to support these tactile internet applications. We want to get this 1 millisecond or 2 millisecond latency. Then the challenge, whether or not we can see, so it translated from bandwidth throughput problem to the latency and link reliability problem. So basically, we can come up with different methods. You can have multiple base stations, or you can have all kind of diversities, to achieve this low latency and also reliable connection.
Yeah, let me just add to that. This was also discussed specifically in the context of the backhaul architecture, how to maintain sustained latency throughput, in light of the potential for, blockage and disruptions. And indeed, the way to go about that is potentially to have some redundancy in the architecture itself by having either multi-homing or having contingency links. I mean, these are some of the possibilities that could be explored to do that.
Right. So it's not only backhaul, right? So backhaul probably is easier. So we talk about
Well, that's not necessarily actually because some backhauls are looked at as potentially as mobile as well.
Right.
My name is Charlie Zhang from Samsung Research America. So thanks for lots of good discussions. Also, I'm sorry I wasn't able to be here yesterday. For the new ideas that's been discussed here, I think there's a lot of good new ideas. But one thing I want to bring up for discussion is we heard a lot about in millimeter wave capacity is a lot because bandwidth is abundant. Therefore, we don't have to worry about spectral efficiency. I think it's a good time to debunk that. It's always about spectral efficiency. It's time we focus on that. We have learned from the actual implementation and trying to commercialize that. Because why it's important? It's intimately related to the bottom line of the business. So yesterday in GovCon, we had a discussion. Some operators from Europe was questioning, is there a business case, for example, for fixed wireless access? It seems to be, from their analysis, it's more expensive compared to using the existing wireless fiber services. So it's probably true, all depending on what kind of assumption you make and how you do the analysis. But ultimately, it's also about what the capability of this millimeter wave service. What is the coverage? What is the capacity you can achieve? And to do that, we really need to think about technologies in millimeter wave that can take us to the next level. I think initially it's also maybe us in industry and together with professors, you guys here, we're thinking about, okay, let's take the first step. Let's not worry about the spectral efficiency and just move this thing forward. At that time, it's the right thing to do because we do not have the technology on the component level. We do not understand system architecture. Everything is new. But right now, I think we have a good first understanding. It's really time for us to really squarely focus on the real goal. We need to make the spectrum efficiency at the same level as lower band at some point in 5 years, if not 5 years, 7 years, or 10 years. I mean, if you look at the efficiency today in lower bands, yesterday, I think also in Globecom, I heard some companies was able to do 24-layer massive MIMO, FD MIMO. They got 20 bit per second per hertz, whereas we are looking at 1 bit or 2 bit. That's not enough. We need to get it higher. Thank you.
Just a quick follow-up to that. Another way to think about it is, if you keep spectral efficiency as your objective, then there are other areas that you can actually start relaxing a little bit. For example, if the per-link spectral efficiency has been increased, then you can simplify deployment by allowing for a lot more relaying or wireless backhaul to actually improve the coverage. So fundamentally, improving the per-link efficiency or the multiplexed efficiency has ramifications on the overall network deployment and overall cost of operating the network. So I think, there's no doubt that that is a valuable metric to continue to look at.
Okay, well, I think this would be the last one so that we can segue into that.
Thank you. And I actually just wanted to emphasize a little bit more on what Charlie said is that, yes, we do understand there is a lot of spectrum in millimeter wave, but that doesn't mean that you actually want to use all of the spectrum, because more spectrum implies a higher noise bandwidth, which always cuts down your coverage. It also means hardware complexity from a device implementation point of view. So I do agree that if we can utilize and get the same capacity by using half or 1/4 of the spectrum, I think it does have a lot of value.
Okay, great.